Let's review what we've done so far. So assume that f maps D to C. D is a domain, meaning it's open, non-empty, and path-connected, and f is continuous. So this is kind of a small set of assumptions that makes it easier to describe what we've proven so far. The assumption that D is a domain, in particular that it's path-connected, is actually not that strong of an assumption for what we're going to talk about. If D were not path-connected, if it were made out of a bunch of little islands, then you could always restrict your function to one of the islands and focus on just that one. Then there you would have the domain of the function being a domain, and then you could apply the discussion. So don't think of this as a very strong assumption. So I'm making that point because we're about to put some actually strong assumptions on the domain of our function. All right, so very early on, right after we defined contour integrals, we observed, due to the fundamental theorem of calculus, that if f has an antiderivative, if f is the derivative of some capital F, then all contour integrals along closed curves, meaning loops or piecewise differentiable curves that start and end at the same place, all of those vanish. So that's just due to the fundamental theorem of calculus. Then we took some effort to also prove a converse for this. So if all contour integrals along loops vanish, then there exists an antiderivative. So if you want to answer the question, is there an antiderivative, then here's a good criterion for answering it. If a function does not have an antiderivative, this is an easy criterion to check because all you need to do is find one contour integral along just one loop that is non-zero, as you've done for, the function 1 over z on the entire complex plane, or the function z goes to z bar. All right, so it seems that in order for f to have an antiderivative, to be the derivative of something, it has to do something pretty special, have all of these contour integrals along closed curves vanish. Another special thing that f could do is be analytic. We know that's special. That means the real and imaginary parts of f have to satisfy a PDE system called the Cauchy-Riemann equations. Okay, so if f is analytic, then does that imply that f has an antiderivative? Well, if we want to know whether this implies this, we can go through this handy criterion that we now have. The question is, if f is analytic, then can we prove that all contour integrals along closed curves vanish? Well, what we've done so far is prove that all contour integrals along triangular paths that are closed, that start and end at the same vertex, do vanish, as long as the triangular path has the triangle and the inside of the triangle fully inside the domain of the function. So that's something, but it's still not the upward implication that we want here. So that tells us that for some certain special closed curves, the triangular shaped ones, for which the inside of the triangle is fully inside the domain, for those we get that the contour integral is zero. But what about other closed curves? So we sort of, so far it looks like we haven't really made progress towards proving that if f is analytic, then it has an antiderivative. Okay, so what will we do from here? Well, it turns out we cannot prove this upward implication without more assumptions, specifically about the domain, some heavy assumptions. So we will assume D is not just a domain, not just open, non-empty, path-connected, but a star domain, which is something I'll define in a moment. With these two assumptions, then we will be able to prove that contour integrals along closed curves always vanish, and so f has an antiderivative. All right, in order to run this proof for analytic functions on star domains, we're going to need to use triangular shaped paths, and we'll try to make a general argument for all closed curves by building off of our result for triangular shaped paths. Okay, so what is a star domain? So whatever it is, what I'm claiming so far is that it's some kind of special domain such that if a function is analytic on it, then you know it has an antiderivative. But here's the definition. A star domain, let's say B, or is an open set, D, such that, let's focus this on the complex plane, such that there is some, let's call it Z sub star in D. So D has to be non-empty, but I'm about to describe how this Z sub star, this point, is special. This point is going to be called, by the way, a star center. Such that for all points Z in D, the line segment joining Z star and Z is fully inside of D. So I have this notation for the line segment joining Z star and Z. Technically this is a parameterized path, but let me just take advantage of the notation. Alright, so by this notation I mean the range of this path, or the actual points along the line segment from Z star to Z, is fully inside D. Okay, so let's look at an example. So take this blob, including the inside, in the complex plane. Then this point could be used as a star center. So if I call this pink point Z sub star, then let's verify that it serves as a star center and therefore makes this set a star domain. Okay. So the idea is that if I take any other point, so here's a random point, in the set D, then the line segment joining that point to the pink point is fully inside of D. So just check enough of them and you might be convinced by the picture. Of course, usually when we're doing things, our sets are not defined by pictures, but they're defined in some formal way, and then it becomes something that you have to prove if you want to show that a certain set is a star domain. Alright, so hopefully that's somewhat convincing that if I just take a random point in D, the line segment joining it to the pink point will be fully inside of D. That pink point is not the only star center, so you could imagine if I had chosen something, some other pink point close to it, that could also have served as a star center. So star centers definitely do not have to be unique. That's why we say a star center, not the star center. But also, only some points are star centers, some points are not. For example, if I tried to use this as my Z sub star, that would fail to demonstrate that D is a star domain. Because, for example, if I take a point here, then the line segment joining them exits the set D. Alright, so there just has to exist one viable pink point to make D a star domain. It should remind you a little bit of the definition of convex, if you have seen that or if you remember it. The fact that there exist 2 points in D such that the line segment between them is not fully contained in D tells you that D is not convex. So this sort of jutting in part makes D not convex. Being a star domain is weaker than being convex. So being convex would certainly imply that your convex sets are always star domains. All right, a good example of something that's not a star domain that has come up a lot is C bullet, our notation for the complex plane with the origin removed. So if I remove the origin, then there's no point in the complex plane with the origin removed which has the properties of a star center. So take any point, no matter where I put this pink point, there are going to be some points in C bullet, namely the points along this ray, which are sort of out of view. Their visibility is blocked by this missing point. The line segment joining this pink point to any of the points along this ray does not stay fully inside this set. So this set is not a star domain. Not just because of the failure of this point to be a star center, but because any pink point you pick fails to be a star center.